All right, so this is part 4 of chapter 7, Entropy. So let's continue with the rest of the slides of this chapter. All right, so now let's develop a very useful relation for steady flow devices. So before that, we need to go back as a refresher. You remember that in a closed system that we considered in previous chapters. So we said that for a closed system, for a quasi-equilibrium process in a piston cylinder, the reversible work or the maximum amount of work for a quasi-equilibrium process is equal to integral of PdV. So before we said that quasi-equilibrium means that a very slow process. So that's sort of equivalent to being reversible. So now we want to, so this was for a closed system, right? Now we want to develop a similar equation for a steady flow device. A steady flow device is like similar to a turbine, a pump, anything which operates on a steady flow condition. So in the steady flow condition, the change of the energy inside the control volume is equal to 0. So now let's say we go ahead and write the first law of thermodynamics or the energy balance for this steady flow process. So energy in is equal to energy out, or the rate of energy in is equal to the rate of energy out. And no energy will be stored in a steady flow device. So energy in, let's assume that Q is positive when it comes in, W is positive when it actually done by the system on the surrounding. So W is energy out, Q is energy in, and then we also do have dH, which is equal to the differential of the entropy coming out minus entropy going coming in. And then we also consider the changes in the kinetic energy and potential energy. So in other words, this is simply equal to Q in plus m dot H plus kinetic energy plus potential energy is equal to energy out, which is work plus m dot H out plus kinetic energy plus potential energy. So that's based on the first law. If we start from the complete form of the first law and just consider write everything per unit mass and take into account the fact that it's a steady flow process, so no energy is stored, we will get this equation. Now we go ahead and consider an internally reversible process. So d delta Q is equal to TdS for an internally reversible process. We also have this relation, TdS relation, second TdS relation, which is always valid, regardless of the process or system or control volume, reversible, irreversible. If we combine these two equations, we see that delta, that's in the differential form, right? Delta Q reversible is equal to dH minus VdP. Now if we go ahead and substitute this equation in the first law, we see that instead of delta Q reversible, we will have delta dH minus VdP. So dH will cancel out from both sides, and then if we rearrange the terms, we will see that W reversible is equal to minus VdP minus delta kinetic energy minus delta potential energy. If we integrate, then the total work per unit mass is equal to the integral of minus VdP minus delta kinetic energy minus delta potential. So this is uppercase delta, means it's the integral of the lowercase delta for instance, for potential energy or kinetic energy. So, all right, now this is the general form of the equation for the reversible work on a steady flow device. So if the kinetic energy and potential energy can be neglected, which is often the case, for instance, in turbines or like compressors or pumps, then we can say that the reversible work for a steady flow device is equal to the integral of minus VdP. So this is very similar to the integral of PdV, but for the steady flow device, it's integral of minus VdP. PdV VdP. Okay, so if the fluid is incompressible, for instance, in the case of a pump, then the specific volume is a constant. It comes out of the integral, and then we can evaluate the integral of dP, which is P2 minus P1 in this equation, and kinetic energy and potential energy. This equation, for instance, can be used for a pump. Also note that in some cases, some steady flow cases, for instance, liquid through a device that involves no work interaction, such as a pipe section. If you consider a pipe section, a flow comes in, goes out, there's no pump. Let's say that in a section there is no pump, and because it's reversible, therefore there is no friction loss in the pipe, and there is no pump to perform work, therefore the reversible work is equal to 0. So the left hand side equal to 0, therefore the sum of the terms on the right hand side is equal to 0. If you look at this, this is the change in the pressure work, the change in the kinetic energy, and the change in the potential energy. If, for instance, the tube is not horizontal, if it's tilted, then Z1 and Z2 would be different between two sections of the pipe. So this is actually called the Bernoulli's equation in fluid mechanics. So based on Bernoulli's equation, for a frictionless flow, frictionless means reversible in thermodynamics, then the sum of the changes in the pressure work, kinetic energy, and potential energy does not change from one section to the other. So for those who have fluid mechanics in parallel or concurrently with this course, they better understand the situation. So for those who are going to take fluid mechanics later, so later they will see and appreciate the use and importance of the Bernoulli's equation. So in fact, thermodynamics helps us better understand fluid mechanics as well. So these concepts are interrelated. So this is a very important slide. So let's summarize the slide again. For a closed system with boundary work, the boundary work is equal to PdV. So the boundary changes. It's a piston cylinder or any closed system undergoing a quasi-equilibrium process, very slow process, expands. The work is integral of PdV. If we do have a steady flow device, so the flow comes in, goes out in a steady condition, so no energy can be stored in the system. If we write the first law and use some other relations for the reversible process and also the first TdS relation, we end up with this equation for the work done during a reversible process. This is work done, so based on the sign convention, it's equal to this obtained by this equation. And finally, we said that for a section of a pipe, there is no work done by the system, therefore the reversible work is 0. And if the specific volume can be assumed constant, then the integral can be performed, it becomes simply Vp2 minus P1. And as a result, we will see the Bernoulli's equation, which is valid for a frictionless process. In fluid mechanics, what we call it frictionless. In thermodynamics, we call it reversible. So when it comes to when it comes to flow in a pipe. So we just found a relation for the reversible work, which was equal to the minus integral of VdP plus kinetic energy and potential energy. So if we neglect the kinetic and potential energy changes, then we will only have negative integral of VdP. So that's for the work done by the system. In the case of a compressor, work has to be done on the system. Therefore, we drop the negative sign and we use this integral with the positive sign. So now let's say we want to evaluate a compressor. We want to evaluate this integral for a compressor. If we assume that the process is isentropic, so from the previous lecture, for an isentropic process, PV to the power of K is a constant. So this is similar to a polytropic process in which PV to the N is a constant. So if we go ahead and perform the integral, so for the work of the compressor coming in, the integral of VdP has to be evaluated. So how to do that? So we do have a relationship between P and V. So we can go ahead and substitute V from the isentropic relation here and then perform the integral. This is very similar to the integral that we performed, integral of PdV in chapter 3, if I remember correct, for a polytropic process. So we performed the integral in that chapter. It's very similar. So the result is equal to what you see here. And if we rearrange it in terms of convert the temperature ratio into the pressure ratio for an isentropic process, we will get this equation for the work required by the compressor. So this is for an isentropic process. For an isothermal process and for an ideal gas, PV is equal to RT, and if it's isothermal, PV is a constant. So we can go ahead and perform the integral again, but this time V is equal to a constant divided by P. So the integral will be in the form of log of P2 over P1 if you perform the integral. So we do have two relations here. One is for an isothermal compressor, the second equation, and one for isentropic compressor. If we show these functions on a PV diagram here, P as a function of a specific volume, if we show these processes like between P1 and P2, so we see this kind of relationship. So for an isentropic process, this curve is represents the process, and then for isothermal, the inner curve, and then for a general polytropic process, the one which is in between. So what we are going to do with these curves. So the integral of VdP, which is the required compressor work, is actually the area under the VP curve. So in this case, the area is actually the area between the curve and the y-axis, because it's the integral of VdP, not PdV. So if it were the integral of VdP, the area would be between the curve and the v-axis. But since it's the integral of VdP, the work done is the area under the curve and the p-axis. So let me hatch it so that you can see the amount of this work for an isothermal compressor. So if the compressor is isothermal, this is the amount of the work, the integral of VdP. And you see that for an isentropic compressor, the area under the curve between the p-axis is the largest. So for the case of compressor, in order to minimize the work, the input work, the isothermal compressor is the best because it requires the minimum amount of work. So based on this analysis and based on the area under the V and P curve. Okay, so all right, so isentropic efficiency of turbine. So we know that the isentropic process involves no irreversibilities. So the process is reversible and serves as the ideal process for adiabatic devices. So if these devices are adiabatic, which is usually the case, like for a turbine, so for an adiabatic device, what is the best adiabatic device in terms of the efficiency, thermodynamic efficiency? So the best adiabatic device is a device which is also reversible. So meaning that the friction effects is minimized in the device. So that's the case for turbine, compressor, pump, and nozzle that we are going to talk in the next couple of slides. So for adiabatic devices, the ideal device is a device which is also reversible. Therefore, the device is isentropic. So this isentropic device is like our ideal device, and then we do have the actual device, because in reality the process cannot be reversible. So therefore we do have actual device and we do have isentropic, which is the ideal. So as a result, the isentropic efficiency of the turbine is defined as the efficiency of the actual device with respect to the efficiency of the ideal device. So what do we expect from a turbine? From a turbine, we expect we use a turbine in order to generate work, and then the work drives the generator. So therefore, the efficiency of a turbine is simply equal to the actual work per unit mass here divided by the isentropic work, because the isentropic work is the work produced from the ideal device, which is the isentropic device. All right, so therefore the isentropic efficiency of the turbine is equal to WA, work, actual work, divided by WS, the isentropic work. So how to find the actual work and isentropic work? From the first law of thermodynamics. So for a turbine is a steady flow device, so energy in per unit time is equal to energy in per unit time is equal to energy out per unit time. So energy in is simply H1, energy out is H2 plus W actual, or double plus WS for the isentropic turbine. As a result, the turbine work is simply equal to H1 minus H2. And everything here is per unit mass. So the isentropic efficiency of the turbine is therefore equal to H1 minus H2A actual divided by H1 minus H2S isentropic. We can show it on Mollier diagram, HS diagram. So if this is P1, the inlet of the the inlet of the turbine, and this is P2, the inlet, the outlet or exit of the turbine. So H1 minus H2S, which is the ideal process, moves on constant entropy line. So it's a vertical line perpendicular to the s-axis. H2 minus H1 minus H2S. But in reality, the entropy will increase. So for the actual turbine, the entropy will increase, and point 2 will be this point 2A, the actual point 2, but on the same pressure line. So visually this H1 minus H2A and H1 minus H2S can be seen here. So as you see this vertical line, the projection of this vertical lines on the h-axis shows us WA and WS. So WS is simply H1 minus H2S, and WA is the projection of H1 H2A. That is the vertical projection of H1 H2A on the h-axis. So we do have a similar concept, very similar concept for a compressor and also a pump. The difference is that for the compressor and the pump, work is actually given to the pump and compressor. Work is not generated, work is input. So the efficiency, the isentropic efficiency of a compressor is therefore equal to isentropic work, which is the minimum amount of work required for an adiabatic compressor divided by an actual compressor work. So based on the assumption that the compressor is adiabatic, a compressor which works in a reversible process requires the least amount of work. So that is W isentropic WS. If we compare it to the actual amount of work divided, that ratio is the isentropic efficiency of the compressor. Again, the assumption is that this device is adiabatic. For an adiabatic device, a device which is reversible is the best. So adiabatic reversible, therefore isentropic device is the best under the condition of adiabatic device. But from previous slides, we noticed that an isothermal compressor actually needs less work than isentropic compressor. So we need to be careful about what we are talking about. We are talking about a device which is adiabatic for sure, and then we say that if it is also reversible, so together adiabatic plus reversible is isentropic, and that's the best device under the condition of being adiabatic. So if you want to show it on the HS diagram, the same story. From the first law of thermodynamics, delta H is equal to the work of the compressor per unit mass. So for the inlet pressure P1 and exit pressure P2, the vertical line here is entropy constant line. This is H2S minus H1. That's the minimum amount of work, isentropic work, if we put it in the numerator. And the actual work is H2A minus H1, the projection of this line segment on the h-axis. For a pump, again, it is defined as the isentropic work divided by actual work. So for the isentropic work of a pump, we can still use like H2S minus H1, but we also derived an equation for steady flow devices, and we proved that the reversible work of these steady flow devices is equal to the integral of VdP. So for a pump, a specific volume is a constant, so that integral becomes Vp2 minus P1. And for the actual work, we cannot use that integral, we just write it as H2A, the actual entropy, the actual enthalpy at the exit minus H1, the entropy, the enthalpy at the inlet. And another device, steady flow device, nozzle. So how to define the isentropic efficiency of a nozzle? So we need to look at the purpose of a nozzle. So why do we use a nozzle? We use a nozzle in order to accelerate the flow and increase its kinetic energy. As a result, the efficiency of a nozzle is defined as the actual kinetic energy delivered at the exit of the nozzle divided by the isentropic kinetic energy, or divided by the kinetic energy under the condition of nozzle being isentropic. So again, here the nozzle is adiabatic and reversible. So if we look at if we write the first law of thermodynamics for a nozzle, we see that at the inlet of the nozzle, the energy coming in is enthalpy. If we neglect the kinetic energy at the inlet, and if we assume that the nozzle is leveled, so there is no change in the potential energy, so that this H1 is the energy coming in. Then it is accelerated, the energy going out is H2, and then the rest of the energy is kinetic energy because the flow has been accelerated. So this kinetic energy is now significant, so we need to consider it. If the nozzle is a real nozzle, then we put A to denote the actual nozzle. For the case of isentropic nozzle, this A becomes S. So based on this equation, we see that the kinetic energy per unit mass is simply equal to H1 minus H2. So the efficiency that we have defined up there can be also written in this form. So isentropic efficiency of nozzle is equal to H1 minus H2A actual divided by H1 minus H2S isentropic. So we can also show it on an HS diagram similar to the previous cases between a line P1 constant, P2 constant. From 1 to 2S, it's a constant entropy line, a straight line, and then the actual line, and the projections on the enthalpy axis is equal to the kinetic energy per unit mass. So if you look at this example, we do have air coming in at 950 Kelvin. So the cross-sectional area of the nozzle is decreasing. So you see that at the exit, if the nozzle is isentropic, the velocity is 666 meter per second, and the temperature is 748. Then if the nozzle is non-isentropic, or if it's irreversible or actual, then the velocity is less than or smaller than the isentropic velocity. So it means that some of the energy has been wasted and has been converted to heat and converted to internal energy. That's why you see that the temperature of the gas at the exit of an actual nozzle, 764 here, as an example, is higher than the isentropic temperature. The reason is that because of the irreversibilities in an actual nozzle, some of the kinetic energy or velocity is because of friction, viscous effects, viscosity, some of this kinetic energy is converted to heat. Okay, so let's stop here.